First of all, I would like to say hello and good afternoon to everyone. Hope you are doing fine and taking care in this pandemic time. So myself, I am Rohit. Today, I'm going to give the webinar about simulators for the autonomous driving system. So let me tell you the agenda for this. So we'll be starting with the introduction, the motivation that why we need simulation in autonomous vehicle. Then we'll move to areas of development. So these will be the areas where the simulation can take place in autonomous vehicle sector. Then I will explain you certain benefits of simulation. So this will be the first part where I'll be talking about a bit of a simulation and why it is necessary and the benefits. And in the second part, I would like to go a bit more in detail in terms of explaining you the simulators that are currently used in the autonomous vehicle research and certain standards that are used. With that, I will also explain certain examples for an open source simulator, which perhaps you can try it on your own as well. And then finally, I will be describing few career choices that can be chosen in this autonomous driving sector in simulation field. So starting with why do we need simulation in the autonomous vehicle or self-driving car project. So as you guys have heard that autonomous vehicle has been uh, around us for quite a few years now, and we have been it is aimed to improve the driver safety and traffic congestion. It will improve the driver safety by reducing the accidents and traffic congestion by, if we have a better flow of vehicles, then the traffic will be less and it will save more fuel, which will be eco-friendly. So just 2 years ago, the future was bright, and the autonomous vehicle were developing fast. Most autonomous vehicle OEMs, tier one suppliers, and hundreds of startups around the world were pushing this concept of autonomous vehicle aggressively and bringing the autonomous vehicle or self-driving cars on the road. Traditional OEMs or traditional autonomous industry was bit hesitant, bit cautious at the beginning, but with the investors' money and the need for the future mobility, they also started investing in this field. So it was going all well, but in 2018, a certain incident happened that caused a lot of havoc in this field. So in 2018, in Arizona, Uber's self-driving car had an accident. In this accident, a woman crossing the street got killed, and because of this tragic incident, the reaction from the public towards the self-driving car, not only on Uber but the whole self-driving car community, was affected, and people started having doubts. So there were lots of challenges in development. So earlier, when this design was conceptualized, it is now been visualized, and we can see it in a testing form. We can see it on the road, and it needs to be tested well. And when it has started testing, there have been lots of questions that, safety of the people, are people really safe on the road when the autonomous vehicle are running or not? So this question have been raised during these past 2-3 years a lot. And because of this, there have been many various challenges in convincing people that this system that we are producing is really safe. So it is very important that the system that we are producing is safe, and it is not just what we are saying, but we are able to prove it. So how can we prove that our system that we have designed is so one way that Mr. Akio Toyoda from Toyota Industry said that, for the autonomous vehicle to be completely self-driving, completely autonomous, it has to have 8.8 billion miles of testing. It would require 8.8 billion miles. So in that, this testing includes both testing on the road as well as simulation. So 8.8 billion miles is a big number. And just to give you like idea that this number is so big, that in last 10 years, Google's self-driving car project, Waymo, has traveled 16 million miles on road. So if we just take this rate, it will take more than 200 years just to get the car on the road, just to prove that that we are capable of achieving that. So this is really, if we just rely on road testing, it is going to take us a lot of time. And moreover, from the uber accident incident, we can understand that when the program is tested on the road, it is very hazardous. It can turn wrong and we can have accidents. So it's a safety issue as well. So the key thing here to realize is that a simulation is a better way to go about. And in simulation, you can also control the attributes, the behavior of the environment, which you cannot do in real life. So in real life, you cannot control the scenario where the person walks in or not, the whether the any uncertain thing happen with you or not, and we cannot really achieve that. But in simulation, we can achieve that, and that's the main advantage, I think, that the simulation offers. So to summarize, I would like to say that in terms of simulation, simulation is necessary because we need a lot of road testing, a lot of testing of scenarios to make our autonomous car, self-driving car, to be autonomous. And in this case, so we'll require that. And then in simulation, if so in simulation will is a solution for it. So we can test the various vehicles at the same time and get those required number of miles. So the areas of development. So in this topic, I'd like to tell you that there are few sectors where the simulation can help us. So the sectors in which we can perform simulation and improve our autonomous driving technology are, the first one is scenario testing. So as I mentioned, there are various scenarios in autonomous driving, like crossing the road or changing the lane. So these scenarios can be tested in simulation. That's the first kind of simulation testing. The second is developing a software algorithm or modeling development. So that's the second, where you will be developing a software for, let's say, object detection or localization or mapping. In the third one, you'll be doing a functional safety analysis. So in the it's you will be doing testing your it's a risk management sort of thing. So for a given module, you'll be testing its extremities, whether it fails, under what condition it fails. So you can do this in simulation as well. Moving on, in the fourth category, that is sensor performance. In sensor performance, you will be modeling the sensor. So sensor modeling is very important for simulation, because we need to replicate behavior of sensor in real life. So we usually model the sensor in simulation. So and this modeled sensor needs to perform like the real sensor. So testing the sensor performance in simulation is one of the key areas as well. And then fusion of the sensors. So there are a lot of things that needs to be done in sensor performance. The fifth and the sixth are electronics and semiconductor, which are the key components of the whole autonomous system, which supports the main brain or main computing power of the autonomous system. So this their optimization in terms of optimizing the signal strength or structural electromagnetic reliability, or the electronics of it, the or cooling for, say, so improving these, optimizing these factors of the supporting components in the autonomous vehicles can also be done in simulation, and these come into category number 5 and 6. But in this webinar, I would like to focus on 1, 2, and 4, that is about the scenarios, then modeling of sensor and sensor performance, and finally some software algorithm and the testing of the algorithms and validating our algorithms. Moving ahead, we will start talking about simulators and what are the benefits of simulation. So the thing is, with simulation, I would like to mention a fact over here. So the US study, in a US study, it was said that, US study says that in 140 million miles, 140 million kilometers, one accident occurs in per day. So if a human drives a vehicle, you require 140 million miles for one accident to occur. So our test system, our autonomous vehicle should perform better than this. So you require at least 415 million kilometers without causing a death. So this is a sort of a benchmark that has been kept. So if our autonomous system is able to drive 415 million miles without any death in simulation or road testing, then we can say it is at least as good as driver as the human. So we will try to achieve this, we are using simulation. And this can be tried in simulation with various various of its advantages. So as I was saying, that these are economical. So when you use do the real road testing, you require the vehicle. And as I said, that there are billions of miles to cover, so you will be having 200 fleet of cars, or at least 200 hundreds of fleet of cars. So in each fleet of car, at least a fleet of cars at least cost 100 million US dollars. So a car, usually a self-driving cars whole project, including the sensors, the electronic components, and the vehicle design, and whatnot, all this everything together cost at least 100 million for, let's say, 200 car fleet of cars. So that can be really cut down in simulator. So you can replicate this and even replicate more number of cars in clients, and you can get the economical benefit, so you don't have to spend that much of money. And second point is to accelerate time to the market. So definitely, if I can run more than 200 vehicles, if I can run thousands of vehicles at the same time 24/7, then I can get more million number of miles. And then the I can accelerate the progress, I can bring the product faster into the market. So another thing is, like, I have to mention that in simulation, as I said, that we can test the scenarios which are not possible to test in real life. So such as accidents, such as close calls, which happen rarely, but which when happen it are fatal, and we cannot really recreate them. But in simulation, we can tune the parameters, we can tune the velocity, we can tune the speed, we can tune when the non-performing characters, such as pediatrician enters. So you can control these aspects of simulation. So that's the key advantage that you get. And additionally, you can test your module. So you can test your module, let's say object detection module, or localization module, and see how it performs in the simulated environment. Is it ready to be used in a road testing? So we can avoid such uber accidents, or the accidents that are occurring due to autonomous cars. So these are the key benefits I like to mention about the simulation and the simulator. With this, I'd like to conclude the first part of this webinar, saying that why the simulation is necessary and the benefits of simulation that we get in autonomous driving. So moving on, I would like to start with the simulators that are used in autonomous industry, and some of the standards that are used in the simulator in autonomous industry. So the first thing that needs to be realized here is that uh, autonomous vehicle simulators are different from traditional vehicle simulations, in sense that apart from the vehicle, you have many other characters that are important, non-performing characters, such as environment, let's say the lightning condition, the sunrise, nighttime, daytime, then the pediatrician, the pediatricians, and then their walking style. So these non NPCs are really key as well. So when you design an environment, these aspects are also important, apart from the actor itself. So we have so much of these possesses a challenge while building a environment. So while modeling the environment, how realistic you make is becomes a question. So the more realistic you make, it becomes more computationally heavy, and then it takes more time as well for the any simulation to run. So that becomes a challenge as well. There are various standards that are used in the simulators. So the standards, so I'm going to mention two standards now. So these standards are mentioned by the ASAM, that stands for Association of Standardization of Automation and Measuring Systems. So ASAM is an organization where many vehicle manufacturers and researchers have come together and formed these organizations. And this organization is used so that they can maintain a standard, and the data transfer can be happen on a common ground, so that all are working on a same level, and the research can be shared. So the two standards that I would like to mention is, first is Open Drive. So the first standard that I'm mentioning here is Open Drive. So Open Drive is a logical road network description. So what I mean here is that in this case is you know in while building an environment, road is very important aspect. So there are road conditions such as you have to model the road condition, that what is the length of the road, what is the width of the road, does it have a footpath on it, what is the speed limit of the road. And then these aspects of the road are important. And not only that, even modeling the surface of the road. So in terms of to get the vibrations from the brake or the suspension system. So for this designing the suspension system, so road surface is also important. And apart from that, you have in an urban system, you have a multiple lane roads or intersection. So roads in general are very important, so they have designed a standard for it. So how you will be labeling your roads, how can you label your system, how you can label your layout in the environment. So they have described a standard for that, and it is called an open drive standard. So in Open Drive is basically an XML format where you mention the road geometry, as I said, the plane elements, vertical profile, width, etc. Then you also mention the logics of the lanes, that is, which is going left, which is going right, and if it is a roundabout, then what is the preference, or what is the logic on the lanes. Then you can also mention the signal and the signal dependency. So each lane can have different signal speed signals and uh, restrictions, so you can mention these as well. And finally, the road surface properties, as I said. So for road surface properties, it is defined by a different standard, but it comes under Open Drive as well. So here you mention the open road surface properties, which are crucial while designing the vehicle. So vehicle in general, the vehicle system, the mechanical aspects of the vehicle. So this will be important there. So this is the first standard. The second standard is Open Scenario. As I've talked a lot about scenarios so scenarios are playing a crucial role right now in the autonomous industries, that in such way that because people have AV manufacturers and researchers have their product ready, but it needs to be tested under various scenarios. So they have created a standard template for it. That standard is called as an Open Scenario. So in Open Scenario, it consists of three aspects or three levels. The first level is that you describe the road network. So as I said, the road network would be defined using the Open Drive standard. So that's the first level. On that, we will be describing the entities. So in the entities, we'll be having the static elements or the non-performing characters, such as the walkers, then animals or cyclists, then static elements such as cars, or let's say if there is a construction going on. So you'll be mentioning these, then as well as the lamp post on the roadside. So all these things will come under the static elements, and it will be mentioned in the entities. So these are the non-performing characters which may or may not affect the scenario. So it is up to you or the scenario designer what you want to include in this in entity form. And the third or the upper level is the actions. So in these actions, we usually put a we create a scenario where where the non-performing character or anything can change. So in this case, for an example, the non-performing characters is trying to overtake our self-driving car. So in the blue, we have our self-driving car, and the scenario is such that the car behind us is trying to overtake lane next to us. So we In this case, in the third layer, we describe the actions of the non-performing characters. So with these three part, we define the entire scenario. So with this standard, you can define various scenarios that can be used in testing the general standard that is used in the research.